Okay, so I'm going to also demonstrate a problem that's similar to the ones 60 through 76 on page 396. So these questions have three parts. Part A asks you to write the equation for the inverse. So this sounds intimidating, but it's actually not that bad, because there's one key thing that you need to remember. If instead of this being a y, it says f of x, what I would do is actually start out by remembering like f of x is the same as y. So to solve a function, or to find the inverse of a function, it's really very simple. You take your original equation and you flip where the x's and y's are. So I'm going to rewrite this as x equals y squared minus 4. Okay, so I've just, wherever I see an x, I'm writing a y. Wherever I see a y, I'm writing an x. And then you resolve the equation for y. Now it seems a little strange, but doing this actually has the effect of flipping your graph, which we'll see when I graph it in a minute, because that's another one of the parts. So, again, I'm going to resolve this for y. So, I'm going to start by adding 4 to both sides. So now I have x plus 4 on this side equals y squared. And then, in order to get y by itself, I'm going to take the square root of both sides. Ugh, goodness, this pen doesn't want to work today. And you need to remember that when you take the square root of something that's squared, in other words, when you're solving for a variable that's squared, this side is plus or minus, okay? And the reason for that is, if you think about it, say if we were solving 9 equals y squared. So I would again take the square root of both sides, and if you forget the plus and minus, you'll get 3. But if you think about it, negative 3 also satisfies this, right? Because negative 3 times negative 3 is positive 9. So negative 3 is also a solution to something squared equaling 9. So that's why this is plus or minus. Stop that. There, okay. Alright, so hopefully that makes sense. Now when we go back to this, so now my inverse, equation for my inverse, is just y equals plus or minus the square root of x plus 4. Okay, so now part B is to graph it. And I'm going to be hand sketching this, so I apologize because it's going to be a mess, because I cannot draw. Okay, so if you remember from previous weeks, the whole point of having you do that section with the shifts and the stretches and all that stuff was to make graphing these a little easier. So again, if you remember the basic shape of what x squared is, which is a parabola, right? So I don't want to actually draw it on here, but if you remember, it will look something like that. And if we've got a minus, so that's not included in what's being squared, meaning instead of something like this, it's on the outside, this represents a vertical shift. So the parabola is getting shifted 4 units down. So, 1, 2, 3, 4. So it looks like just a regular old parabola, but instead of intersecting at the origin, the vertex is down there. Okay? So that's my original graph. And now I need to graph this one. So there's 2 ways that you can go about this. You can calculate points and graph it that way, or you can, and I'm not expecting you guys to be precise on this because it's a little tricky, but you can do the kind of cheat shortcut and imagine that there's this dotted line that runs diagonally through the origin, right? So, and this line represents the line y equals x. So you can sort of cheat at drawing an inverse by just reflecting your graph across this line, which can be a little hard to picture. But what I would do is just kind of pick some points along your graph. and then they'll just go in the same, like it's the same distance away on the other side of the line. Like for example, that point on this parabola. So, and again, this needs to be your reflection. I probably shouldn't be drawing, but anyway. So, that point, or this line from one point to the other, needs to intersect this one at a 90-degree angle. So that might help you sort of envision where the point needs to go. And then, obviously, it'll cross there. And then again, if I pick this point at random, okay, that looks like it's due to do about right here on this side. Oh, actually, that's a little off, but that's okay. And then if you just keep going, so, and whenever you see a point on the axis, I recommend that, because that one's easy to do. So this one, again, is the same distance as it is over here. And then again, I can just keep picking some at random, so that one is about right here. And this is not turning out very well because I'm a horrible artist. So, and then this one will be, again, right angle, so about right here, needs to cross the x-axis. So you can kind of see by the shape of my points that this is turning into a parabola, right? At least on this side. If my points were drawn better, and if I could draw, but roughly that's where that point should go, that's where that point should go. So you can keep going, obviously with this, and again it just keeps getting reflected, so this point would be about right here. Oh, I does not want to cooperate this morning. So this point would be about right here, and so on and so forth. So the shapes of those graphs should be roughly the same. Now in this particular case, you can see it looks like this parabola has just been turned 90 degrees. That's not always going to be the case though. You can't just automatically turn the graph 90 degrees and draw it. That won't always work. So I really recommend the kind of figuring out the reflection points and going that way. Or worst case scenario, pick some values for x, plug them in, figure out what y is going to be, and plot it that way. That doesn't really matter. Okay, and so that was part B. So for part C, we need to figure out what the domain and range for both of these functions are. So let's start with our original function, which was this parabola right here. So that was just f of x. So the domain for this one, and again, domain is all possible values of x, or all possible values that x can take, excuse me. So it looks like, based on what I've drawn, that x would stop roughly right here and roughly right here, right? But you've got to try to imagine like what happens as x goes off to infinity. So if you look at this function, there isn't anything that we can plug in for x that would make this function undefined. Okay, that's really what you're looking for. So unless you have some division in there where x is in the denominator, or unless there's a square root in your function, there are no problems. You don't need to worry about it. There's no bound on what x can be, which means that the domain for this one is negative infinity. Oh god, that's a horrible infinity sign. But anyway, negative infinity to infinity. Okay. The range, however, so the range are the possible values that y can take. And if we look at our original function, our function does not dip below where y equals negative 4, right? This graph does not have any part of it that's down below y equals negative 4. So that's kind of where it starts, and then y values increase from there. So our range, and it includes, even though my graph looks terrible, but the way to check to see whether or not this lower bound is included or not is plug it into your function and see if you get something that works. So if we plug in negative 4, I'm sorry, that's the range. If we plug in our x value, at that point, if we plug that in, we got to make sure that we get something that still exists. Okay, so if we plug in x equals 0, we plug that in, 0 squared minus 4, that's a totally valid answer. we'll see in a minute that it's possible to get things that aren't valid. So, anyway, so as long as that answer is a real number, your lower part of your range is included in your function. So, and that's important just to determine what kind of bracket you need, whether it's an open bracket or a closed bracket. So our range would be -4. And again, there's no upper bound on y, so that goes off into infinity. Okay, but we also need to determine domain and range for the inverse of x. And that's the notation for that, by the way. So this I should have actually written as f inverse of x equals plus or minus square root of x plus 4. Okay, so now we're going to look at this graph. And again, looking at domain, we want to see if there are any bounds on what x can be. So if we look at this, well, there are no values on this graph for when x is anything smaller than that. So here's the trick. If you figure out domain and range for your original function, if the inverse exists, it will be the same domain and range as your original function, but flipped. So whatever the range was is now the domain for your inverse function, or whatever the domain was, is now the range. Now, I mentioned earlier about points that don't work. So, for example, say you wanted to check and make sure that -4 is my cutoff point. Well, if I plug in -4 into my inverse function, I would get -4 plus 4, which is 0. And you can take the square root of 0, that's fine. It would just be 0. So, that function has a value that exists at that point. But what if we plug in, like, say, something a little further this way, like -5? Well, if I plug that in, I would have -5 plus 4. That's -1. And without the use of imaginary numbers, we can't take the square root of -1. So that's why the domain for this stops at -4, because it can't be any x value smaller than that, because if you plug that into this function, it won't work. In other words, you enter imaginary land, and we don't like to do that unless we absolutely have to. Okay, hopefully this clears these problems up, but if you do have any questions, please don't hesitate to let me know.